This next video in this series of videos about the NicheMapR Shiny applications, web applications, is looking at the Ectotherm model. It's going to look at this global Ectotherm calculator app. Now, this app is running off the microclimatic model that's I introduced first, which is running off the global long-term average monthly climatology. So it's doing the middle day of each month for the microclimate model, but then the Ectotherm model runs with the input from the microclimate model. And you can see on the left-hand side, as before, we have the controls, and on the right-hand side, a series of plots, but we have some quite different looking plots. Now, I'm just going to run a simulation of a dead animal, an inanimate animal, just to start off with, okay? And broadly, what this calculation is doing is solving a heat budget for an ectothermic organism. So this organism, its body temperature is fluctuating with the environment, depending on what the environmental conditions are, unlike an endotherm where the body temperature is being held as constant as possible. In this case, the animal's body temperature is fluctuating according to the heat exchange. And this model is calculating that heat exchange. It's calculating the solar radiation going in, the infrared radiation coming in, the solar radiation going out. It's calculating the convection driven by the wind speed and the air temperature. It's calculating any evaporative cooling and any conduction with the surface. So full heat budget of the organism. And it's doing this starting off at that site that we started off with, the microclimate model at Uluru. And what this first plot shows is the body temperature that results from that calculation if the animal was simply sitting on the surface all day. So you can see this animal would have a body temperature below 20 at night, and then as it gets warm when the sun rises, you see the body temperature rises to quite a high temperature, to almost 60 degrees, and then cools down in the afternoon. So that's what this plot shows. Now, if we make it an animate, alive organism and run the model again, what it's going to do is each hour it's going to check what the behavioral settings are for the animal. And that includes, does it come out during the day or does it come out at night? And what temperatures does it like to be? And it's going to try and find body temperatures that allow it to be at those target temperatures and active at those times of day. And it's going to behaviorally move in and out of the shade, and it's going to behaviorally change depths. It's going to retreat underground if it needs to, and it's going to go to different depths underground if it needs to. So what you have on the right-hand side, at the moment not showing anything particularly interesting, plots of how much shade is selected and how deep the animal went. So you can see it's at 1 centimetre above the ground, which is the microclimate height that we're running. So that's the height above the ground. It's on the surface, and it's in the open. Now, if we run the model, though, with the thermoregulation going on by clicking this alive option, you can see that the body temperature now is not going above 40, which is actually the critical thermal maximum of this animal. And it's being regulated around the preferred temperature, which is this orange dotted line here. You can see that it's achieving this by choosing shade. So you can see there's shade being chosen between 8 in the morning and 11 in the morning. And then you can see this shade also being chosen between 3 p.m. and 5 p.m. And you can see that the animal is on the surface from about 6 in the morning through to about 11 in the morning. And it's also on the surface from about 3 in the afternoon through to about 6 in the evening. But you can also see that during this gap here, it's gone underground again. So it's gotten too hot in the middle of the day for it to be foraging, and it's retreated underground, and it's retreated up to 15 centimetres below ground to get away from the heat. And if we look at this plot again, you can see these dots are showing when the animal was either basking or foraging. You can see the scale here, or the legend here. So by basking, it's what's meant by basking is that it's out of its retreat, and that means that it's under conditions that are warmer and better for it than it would be if it was in its retreat, but it's not warm enough to forage, so it would be sitting just outside its burrow if it was a burrowing animal. And then once it gets above this foraging threshold temperature, then these gold dots appear, and they are the hours that it's active. Okay, and so that's what happened in January. Now we can have a look at what happened in February. You can see there's still a gap in the activity window in the middle of the day. March, you can see they'd be active throughout the day without a gap to hide underground. Actually, this is not updating for some reason. Just going to run the model again. All right, now it's updated. So you can see it needs shade in the middle of the day, but it's actually able to be active all the time. If we go to a really cold month, June, you can see even in June at this place, they can get 3 hours of activity in, and they'd be basking for 4 hours of the day, but they wouldn't need any shade at all. And you can see they're going down to about 10 centimeters at night, and that's to get away from the cold. So you can see the critical thermal minimum down here. They're avoiding reaching the critical thermal minimum. Now, all this is collated, all this information about activity in this plot here, which is showing on the x-axis the month of the year, and on the y-axis the hour of the day. And it's showing nighttime hours in dark blue, it's showing foraging hours in gold, and it's showing basking hours in light blue. So you can see we're currently looking at June. So here's June. You can see it's nighttime here. You can see that that's going up until the sunrise here. And so it's not active for that reason. And then at 7 in the morning, it tries to put the animal on the surface because it's diurnal, but it calculates that it's too cold. And so the animal's not active at this first hour of the day, or the second, or the third. It's not until 10 o'clock that it's warm enough to come out and bask. And so that's this point here. And it's got a couple of hours of basking, and then 4 hours of foraging, and then a couple of hours of basking. And there's too cold. So you can see that across the year, the foraging window narrows into the middle of the year in the southern hemisphere, and then broadens again. And the total number of hours, if you sum that up over all the days in each month, would be 2,550 hours. And it ranges, the month with the most activity is November here. So this is giving you an idea about the constraints on the animal's activity. If you want to see all the microclimate plots that are underlying these constraints, then you just click on the show microclimate plots, and this will look familiar from the first video. These are the microclimatic conditions in June. And we'll go back to January. So they are the microclimate plots, but of course you want to be able to control the properties of this animal, and that's you can change the microclimate as before. So if you click on this, you can change all the microclimate parameters as before. So it's exactly the same as the microclimate model app, but it's additionally got these parameters for the ectotherm model. So if we click on this, we can control a number of things. We can control the size of the animal in terms of its mass, grams. This is controlling the height above the ground that the animal's at. This is very, very important. We're currently modeling a small lizard, 40-gram lizard, so 1 centimeter is good. If you were modeling a much larger animal like a monitor lizard, like the parenti, which is Australia's largest lizard that roams around this landscape, you might want to have the height set to 20 centimeters or something, the midpoint of the animal. You can change the shape. You can change it from a plate to a cylinder to an ellipse to a lizard to a frog shape. The lizard and frog shape are customized shapes, lizards based on the desert iguana from Warren Porter's work, and the frogs based on the leopard frog based on Dick Tracy's work. But you can consider it an elliptical lizard if you like. You can choose whichever one you want. And there's a stretch factor, which say you choose a cylinder, the stretch factor 3 means that it's going to have a long axis that's 3 times as long as the short axis. So the length relative to the diameter of the shape of the cylinder shape. And just out of interest, if we run it as a cylinder, there's not much change. There's a little bit of a change, but there's not much change to the calculation. Okay, then we have these behavioral constraints. So we can make it diurnal, nocturnal, crepuscular, or any combination of those. So if we thought this animal can come out all the time, let's say a snake will come out at any time of day, and there's a few snakes in this part of the world that will come out at any time of the day. And if we make them snake-like by, say, making it 10 times as long as it is in diameter, and let's make it a 500-gram snake that's active at any time of the day. With those thermal constraints, you can see that there could be a bit of, or at least it'd be out at night at some times of the year with these particular settings. We can also say, can it seek shade? Can it go in a burrow? is the burrow in the shade, and can it climb? So these are some of the behavioral constraints. So if we said this animal can not seek shade, so at the current setup where it can seek shade, it's got 2,795 hours of foraging per year. If we run the model again without access to shade, it cuts down to 765. You can see there's these massive holes in its potential activity time. If it didn't have access to shade, it's spending most of its time hiding in its burrow, getting out of the heat. And, you can very quickly ask what would happen if we go to the microclimate parameters. How much would the activity be constrained if we also made it, say, 3 degrees warmer? So it's currently 765 hours. If we run the model again, if we make it warmer, in fact, it only decreases by a couple of hours because it expands its activity into the evening. Whereas if we said that it's not able to be foraging at night, it's behaviorally only diurnal, then we're going to end up with, well, again, not too different actually in this particular case. It's mainly making up for those hours actually in the winter. So it's having more foraging in the winter. So it does show you straight away how powerful the effect of shade is relative to, say, just general climate warming. Okay, and now if we didn't let it burrow, then we're going to see a very unhappy animal that's basically dying all the time. So they really need access to burrows. And you can say how deep it can access a burrow. So at the moment, it can go between 2.5 centimeters and 1 meter. If we turn the burrow back on and just say that it's only able to get to, say, 20 centimeters and run the simulation again, you would see that would be fine for this animal in January. But if we made it, say, 10 centimeters, then the animal's going to be too hot. So if it can't get deeper than 10 centimeters for whatever reason, it would be overheating. Then we have all of the thresholds for the behaviors. So we've got the minimum foraging temperature and the maximum foraging temperature, which is controlling these dashed lines, the red and blue dashed lines here. We've got the basking temperature. So this is the temperature which it will willingly, the body temperature it will willingly have outside its retreat. So if it can be 20 degrees or warmer outside its retreat, it will go outside its retreat unless it's warmer in the retreat. That's what that does. And then there's this interesting parameter here, which is the body temperature at which it can physically leave the retreat. So it's the get out of bed temperature, if you like. So an animal might be sitting underground where it might be quite cold underground, and if it's not physically able to walk out of its burrow or slither, if it's a snake, and get to the surface, then it can't come out, even though the conditions might be suitable above ground. And that does happen. There are winter days in some parts of the world where it's warm enough for a lizard to be out, but you don't see the lizard, and that's because it's too cold to get out of bed, basically. So that's that threshold. And then there's the critical thermal maximum and minimum, which in this simulation, it's trying to avoid the critical thermal minimum by going deeper underground. And it's also trying to avoid getting near the critical thermal maximum by going underground. And in fact, it avoids getting to the critical thermal maximum. It actually aims to be, the threshold that causes it to go deeper is halfway between what you set the maximum foraging temperature and the critical thermal maximum. So about 37.5. It won't get any hotter than that if it can avoid it. And then you've got the preferred temperature, and they're all the different behavioral thresholds. So we'll always try and get as close as possible to the preferred temperature when it's foraging, if it can, by increasing the amount of shade. If I go back to it being able to seek shade, run the simulation, you can see it's trying to be as close as possible to the preferred temperature here. But again, because it's sorry, I should make it be able to go a bit deeper. Now it's a happier animal going deeper underground. And then one other thing you can change is the solar absorptivity. In fact, this whole kind of model got developed in the first place by Professor Warren Porter because he wanted to understand what is the effect of the ability of, in particular, the desert iguana and its ability to change color, to go quite pale, to be 40% absorptivity, 60% absorptivity at the lowest. So if we change it to 60%, we can ask that question or answer that question. In January, it would have 8 hours of foraging if it was a very dark animal. If we made it 60% absorptivity, so it's a light animal, Well, it doesn't really help at all, actually. So there's an answer to that question, at least for this particular lizard and this particular site, not that much of a difference. Okay, then we can also make the animal into a frog by changing the skin wetness. And at the moment, it's lizard-like. It's almost watertight. It's about 0.1% wet. So that's the fraction of the total surface area that's acting as a free water surface. If we change it to 80%, that's more like a frog. Okay, and what you'll see is that the body temperature now is much, much, much lower because of evaporation. And yeah, finally, there's this heat signal here, which is saying what rate of change of temperature per hour does it need to actually leave its retreat. So this is for simulating activity stimulated by a pulse of heat coming from above, which is an exploratory thing. We don't really know how animals decide whether it's warm enough to come out. They might use they might use an internal body clock, or they might use a heat signal. So that's just something you can play with to explore that question, and relatively unanswered question. So that is the ectotherm model in a nutshell. And again, if you want to, you can save your parameters for the ectotherm model, microclimate model, and site. And you can also save the output. And I didn't really show this in detail before, but if you wanted to get the microclimate output, you just click on this and you'll get a CSV file, which has all the microclimatic conditions. Don't know why it's opening up iNaturalist, but if we go here, you can see it's got a mock date, which is actually how many hours have elapsed since the beginning of the simulation. The day of the year, this is the 15th of January because it's running the middle day of each year. This is day 46, which is the middle day in February. The time in minutes, the air temperature at 1 centimeter with our local height, and at 1.2 meters. The relative humidity at 1 centimeter versus 1.2 meters, wind speed, those two heights, how much snow melt, what depth of water is pooling on the surface, how wet is the surface, what's the angle of the sun in degrees, 90 is below the horizon, what's the solar radiation in watts per meter squared on the flat ground. Remember, that's flat ground, even if you've chosen a slope. This is the sky temperature in degrees C. So if you took an infrared thermometer and pointed it at the sky, that's what temperature you would record. And that's used to get the downwelling long wave radiation for the heat budget. How many millimeters of dew is forming each hour? How much frost, millimeters of frost? Is snow falling? What's the snow depth? What's the snow density? So that's everything that's in the microclimate output file. There's a soil file which will have the same setup, but it'll have the soil temperature at all the different depths. That's what that'll have in it. When the soil moisture model output is available, as it is in the global hindcaster apps, you can get the soil moisture in either soil moisture as a percentage or soil water potential. And then if we go back to the app, and why iNaturalist opened. It's just going to run again with the default settings. But if we go back to the app, run the model, and you get the ectotherm output. You can see we've got the dates, the day of the year. The time is actually in hours here. We've got the body temperature, we've got the shade selected, the solar radiation experienced by the animal, not what was generally available on the surface, but what the animal experienced, the depth that they chose, whether they're active, 0 is inactive, 1 is basking, 2 is active, what air temperature they experienced, what ground temperature they experienced, the sky temperature, the wind speed. When they're in their burrow, it's assumed to be virtually still air and saturated air as well, so 99% humidity. This is the angle of the sun again, the day length. So this is the photo period calculated by the model. What the absorptivity was, it is possible to have it flexibly change its absorptivity behaviorally. What fraction was touching the ground of the body, what percentage. There's also what posture it was, what angle it was relative to the sun. So it could be perpendicular somewhere in between, or parallel, and 0 means perpendicular, 1 means parallel, 2 means somewhere in between. Was it panting? So it's actually got a panting mode, so it can actually lose some heat to cool its head down by panting. How many mils of oxygen was it consuming per hour? It's actually calculating the metabolic rate of the animal with a generalized allometric function for lizards. In the actual R package, you can change that to your specific animal if you want. And then there's the water loss. It's partitioning out the respiratory water loss and the cutaneous water loss in grams per hour. So all that you can get, not all of that, of course, is plotted in the app, but all of that information you can get out of this calculation. Okay. So that's the Ectotherm model. And if I go back to the forecasting and hindcasting tools, there is a global Ectotherm calculator, which runs exactly the same way, but using the output from the global microclimate hindcaster. So, oops, I chose the wrong app there. This one, number 5 in the list. So this one's going to show the calculation of body temperature of the same kind of animal, but in Namibia. It's just loading those calculations. So you can see it's the same set of plots. It's got the activity plot and body temperature plot. It's got the shade, it's got the depth, and it's got the activity window, but it's actually showing every single day of the year for, in this case, 2019. And you can choose a particular month to plot or a particular day to plot. And then this is looking a bit more like the previous app from that point of view. Okay, so that's the Ectotherm model.